Okay, so this next section is about Le Chatelier's principle, and there was a French chemist in the late 1800s by the name of Henry Le Chatelier. He basically said that if we stress out a system at equilibrium, and by a stress, I mean maybe I change the volume, which would change the pressure, or maybe I change the temperature or the concentration of something, then that system will shift. Shifting means I will shift to the left or the right of the reaction, meaning shifting left is going to consume product and produce reactant. Shifting right consumes reactant and produces product. And I'm going to show you what this looks like, okay? So it will shift to partially alleviate whatever stress we have caused to hopefully get back to equilibrium. I'm going to underline the word partially because we will never completely alleviate the stress that we have caused. So that means the concentrations of reactants or products that change, whichever one I change, it will never go back to where it was originally. Okay, it may get close, but it won't quite get there. So what I'm going to do is I'm going to add things and I'm going to take them away, and you're going to see what happens. Okay, so let's take a look at what happens when we add things. So if reactant or product is added to a system that is at equilibrium, then what we will do is we will shift to remove some, I'm going to underline some, of the added chemical. Okay, so let's say I have reactants A and B, and they have produced product C. So if I go ahead and I add some A when I'm already at equilibrium, that's the stress. Okay, anytime you add reactant, you shift to the other side. So since reactant is on the left side, I would shift to the right. Okay, so adding A causes me to shift right, and when I shift right, I will consume reactant and produce product. Now here's the caveat. Even though you are consuming B and A, and C is going up, I will never consume all of the A that I added. Does that make sense? So overall, A still is higher than it was originally. Okay? All right, let's talk about C. If I go ahead and I add C, adding C means I'm increasing the product. I always shift to the other side. Since product is on the right-hand side, I would shift to the left. Shifting to the left will cause me to consume product and produce reactant. So A and B will go up. I will consume some of the C that I added, but not all of it. So overall, C remained higher than it was originally. Okay? All right, let's talk about removing things. When reactant or product is removed from a system at equilibrium, we will shift to replace some of the removed chemical. I'm emphasizing removing or replacing some of it because we'll never replace all of it. Okay, so if I go ahead and I remove B and I'm at equilibrium, since B is a reactant, I always shift towards things that are removed. Okay, so over here when we added things, we shifted away or to the other side. So in this case, when I remove things, I will shift to that substance. Okay? So if I remove B, B is a reactant, so I will shift to the left. When I shift to the left, I will bring up reactants A and B, which means C will go down. I will never bring back all of the B that I removed. So overall, B stays down. Okay, and then let's talk about C. If I remove C, I need to move in its direction, so you will shift to the right. You will bring back some of the C that you had removed, but not all of it, and then you will consume A and B. So A and B will go down, C will come up, but it will never come up to where it was originally, so it still stays lower than it was. Okay? All right, so is this enough of a sort of like overview of what's happening? So let's go to the next page. and let's take a look at some sample problems before we do a practice problem, okay? Okay, here in this sample problem, it says some HI is added. Locate HI in the reaction. HI is a product. So if we had added HI, you want to move away from it. You want to move to the other side. So that means you would shift to the left. When you shift to the left, you will produce H2 and I2. So H2 and I2 will increase. You will consume some of the added HI, but not all of it. Notice it says consume some of the added HI. Okay? Since not all of the HI was consumed, that means overall the concentration of HI had increased. Okay, so once I get back to equilibrium, that's how things would be. Does this make sense? Okay, let's take a look at another. Let's look at this sample problem. This sample problem is showing you calcium hydroxide solid at equilibrium with its ions in solution. So it says that we are looking at a solubility equilibrium. This happens when a solid is in equilibrium with its ions. So that means the rate of dissolving the solid equals the rate of recrystallizing it from its ions. What they did was they removed some hydroxide by adding hydrochloric acid. This is often how they remove acids and bases or hydroxide ions and hydrogen ions. So if I want to remove hydroxide, add acid. If I want to remove hydrogen ions, then add base. Okay, so hydroxide is here on the product side. So we have removed some hydroxide. Anytime you remove something, you move in its direction. So that's why we are moving to the right. We will shift right. The whole point of shifting right is to replace some of the removed hydroxide. You will never replace all of it. So as I shift to the right, that means the calcium ion concentration, which is on the right-hand side, will increase, but I was never able to replace all of the hydroxide that was removed, so the hydroxide ion overall decreased. Okay? All right, let's take a look at some practice problems. Okay, so in 1A, it says they have added some iron 3 nitrate to the system. Iron 3 nitrate, as you know, all nitrates are soluble in water. That means it immediately disassociates into its ions. So we have iron 3 and nitrate ions floating around in solution. The only one that we're concerned about is the one that's actually in the equation, which is the iron 3. So that means this has been added when we're at equilibrium. Anytime you add something, you shift away from it. So which direction will we shift? To the right. Yeah. When you shift to the right, what happens to the concentration of this product? So this FeSCN plus 2. What will that do? Increase. It increases, okay. What happens to the concentration of SCN negative 1 when I shift right? Decreases. Decreases. And then when I shift right, will I consume all of the added Fe plus 3? No. No. So that means overall the Fe plus 3 is higher than it was originally. Okay? So the whole point of shifting right was to consume some of the added Fe plus 3 and restore equilibrium. Okay? So if you were to describe in words the whole point of shifting right, that is it. Okay, let's take a look at number 2. Number 2, what does Le Chatelier's principle will happen if some sodium biphosphate is added to the system? It says the biphosphate ion reacts with iron 3 ions. Okay, so am I adding iron 3 or am I consuming iron 3? By adding this sodium biphosphate. Sodium is an alkali metal, and all alkali metal compounds are soluble in water. That's why that separates into its ions. So if it's reacting with the iron 3, what's happening to this iron 3 ion? Is it going up or coming down?
Decreasing.
Yeah, this decreases. So we are going to remove some of this. When I remove some of it, which direction will I shift?
Left.
Yeah, move in its direction, so shift left. And the whole point of shifting left is to restore some of the lost Fe plus 3. You'll never restore all of it to get back to equilibrium. Okay, now, when I shift left, what happens to the concentration of SCN -1? I'm moving that way. Yeah, it goes up. And then what happens to the concentration of FeSCN plus 2? Decreases. Okay, and then if we bring back some of the Fe plus 3, but not all of it, then what happens to this concentration overall?
Decrease.
It decreased. Okay, number 3, graphing. Okay. We can draw an estimation of what we think is going to happen to these concentrations on a graph. You don't always know what the numbers are going to be, but you know whether they're increasing or decreasing, and you just sort of take your best guess, okay? So when you take a look at number 3, it says, and I'll make this a little bit bigger, look at this graph, and at T1, which is right here, H2 is suddenly added. So do you see how the concentration of H2 just kind of took a spike? So anytime you add something suddenly, you'll have that spike up. If you suddenly remove something, you'll have a spike down. Okay? Equilibrium is reestablished at T2. Complete the plots below. Okay. So if H2 is suddenly added, here's H2, I'm highlighting it in my reaction, and this is what you're adding. Anytime you add something, you shift to the other side. So which direction do I shift to? Marco, shut your computer.
The right.
Yeah, so we're going to shift to the right. Okay. Sorry, when I shift to the right, what happens to the amount of HI?
Goes up.
Yeah, it goes up. Okay, so it's going to go up and level off at T2 because this is where equilibrium is going to reestablish itself. Okay, so I'm going to have this coming up and then leveling off and then staying leveled off. I'm trying. Okay, staying leveled off from T2 on. Okay. What happens to I2?
Decreases.
Yeah. So it's going to come down and then level off at T2. So we're going to come down and then it's just going to stay right there at T2 on. Okay. And then what happens to H2 when I shift to the right? Will I consume everything that I added? No. So what this means is you cannot come down past this point. Does that make sense? So you're going to come down, doesn't matter how far, as long as you don't go past that dashed line where it was originally, and then it levels off at T2.